All right, so today we're going to be talking about structural equation modeling, and I've got here in the title a word salad of words. Structural equation modeling does quite a few different things, so I'm going to talk about some of the things it does, such as path analysis and confirmatory factor analysis. So structural equation modeling, I had a class on this in graduate school, and people kept asking, well, what is it? And the professor said, it's everything, and people kind of chuckled with that answer, but it is almost everything. It's a little bit of, it's regression, but it's also factor analysis, it's path analysis. You can do quite a bit with structural equation modeling. So we're going to talk about what it is in more detail. I'm going to show you some examples to start with. Here, in this first example, we've got a similar type of model that we saw with exploratory factor analysis, but what we have is intelligence, and it's measured by 4 different items or 4 different scales. So we could imagine vocabulary, block design, matrix reasoning, and something else that is being measured to measure intelligence. And when we see squares, and I'm going to talk about this in more detail, when we see squares, we're talking about things we've actually measured. And what we can see here is that intelligence is, in this factor up here, is indicated by 4 different scales. And so what we're looking at here is a confirmatory factor analysis, basically, where we can see that this first scale, maybe it's vocabulary, loads on intelligence at 0.7, the third scale at 0.73, and the fourth scale at 0.82. So we can see the loadings of all the different scales on intelligence. What we've got then below this is, it's labeled E1, so maybe it might be thought of as error, but this is what's left over. This is what's not accounted for with this intelligence factor. So this, we called this last week unique variance. The label, it shows just 2-headed arrows. This is shorthand for what we saw last week, where we had a circle with an error component. It's kind of just shorthand for that. And again, we're calling it error, but it's really just unique variance, things that are not related to that factor. Up here, this double-headed arrow is also a variance, so meaning that there's variance in intelligence scores. What's different about this compared to what we did with exploratory factor analysis, we see another factor, and this is academic performance as indicated by SAT, high school GPA, ACT score, but we see intelligence predicting academic performance. So it's almost as if we have a confirmatory factor analysis here, another confirmatory factor analysis here, and then in the middle we have a regression. So we have intelligence predicting academic performance. So again, this is structural equation modeling. It's a combination of many different things. So we can look at how one factor affects another, and one of the big benefits is that we can measure this, or this factor can be indicated by multiple things. Here's a little bit more of a complicated one. Some of the error terms are just missing, so this is another shorthand. People just usually leave that unique variance off the bottom of these, but we'd have, on each of these, we'd have a little error term that's not associated with the factor. So we have something here, parent psychological health is indicated by positive and negative psychological health. Child psychological health is indicated by positive and negative. We've got self-efficacy beliefs with 2 indicators, and then family-centered care with another 2 indicators. What's unique about this model, though, it's more than just factor analysis. We've got a pretty complicated regression going on where child psychological health is predicted by self-efficacy beliefs, parent psychological health, child special health care, and we have a mediator model in here as well. Let me just erase this, where self-efficacy beliefs directly affect child psychological health, but indirectly affect it as well through parent psychological health. So we can create these more complicated models that are probably more realistic in the real world, versus regression, where we might have a bunch of things predicting one outcome variable. And then this one, it looks even more complicated, but just kind of to show you this, we've got 5 separate factors here indicated, each one indicated by a multitude of variables, and then we can look at how each of these predicts the outcome. So in this one, the main outcome is stress spectrum domains. We've got resilience, emotional coping, predicting, so emotional coping and resilience predicting that, but then we also have a bunch of other variables predicting emotional coping and resilience. One of the things that I'll show you in this model and what will be coming up later, these are fit indices, and this tells us how good of a model we have. So we can, our SCA is thought to be a good fitting model if it's below 0.05, which it is. CFI, the higher it gets, the better fit you have. So closer to 1 is a better fit. So we'll see this often in models too, is just how well it fits the data. And I'll go through that in more detail coming up. Another thing I'll point out is a double-headed arrow between emotional coping and disengagement coping just means they're correlated. And same thing with between positive coping and emotional coping. They're not predicting one doesn't predict the other, rather they're just saying it's correlated. So they don't have any hypothesis about one going in one direction or another. So the big thing that we see with structural equation modeling is these circles, or these latent variables. And these latent variables are things that we'd really like to measure in the real world. We just can't actually directly observe them. So things like depression, it's, we think of depression and we think we can see it, but we measure it with self-report, we measure it with behaviors, we don't actually see it. So they're latent, or things that we don't see, and that's why they're called latent variables. And when we think of latent variables, another way to think about it is the true score model of a measurement. So when we measure something, and there's a lot on this slide. When we measure something, so let's say we get the score from the BDI, this measurement is made up of 2 components. So one is true score, and so that's true depression. That's how much the person is really depressed. And the other part is error. So there's things that person filling out that self-report is talking about or thinking about other things rather than their depression. So there, could be random error, they read the question wrong. It could be systematic error, that really it's measuring something else like negative affect or anxiety or something else that's not part of depression. So this is one way to think about it. This is the same, I'm just putting it in the form of a latent model. So we have our measured item, where we always put a square around things we actually measure. And it's made up of 2 components. The true score, which we would like, this is the latent variable that we would like to measure. And then it also has an error, or things that are not related to that latent construct we'd like to get at. So ideally, when we do this, there are problems with just having one measurement to measure that construct. So when we think of something like depression, we would want multiple indicators. We want the cognitive component of depression. What's the person thinking? The behavioral component of depression. Maybe the physiological. Maybe we'll measure cortisol or some other things we'd like to measure. So the more indicators we have, the better it's going to be for measuring that true score. So here's an example, and we can think of a bunch of items. So let's say this is all items related to depression, and they correlate with each other. So we've got all these double-headed arrows which indicate correlation between these different items that we've measured. If I get rid of these correlations and we create a factor model instead, it looks something like this. And we have a latent construct, maybe it's that depression that I've been mentioning, and this latent construct of depression is indicated by these four different variables. And when we do this, we get these factor loadings, and these are kind of indicative of how much each one of these variables are related to this measure of, or this latent construct of depression. So this fourth thing that we've measured is a little bit higher than the other one, so this is probably more related to that construct that we're measuring. And then we have our error term or our unique variance, whatever is left over that's not part of depression. So again, when we look at latent factors, it's a better thing to do than what we usually do of just measuring it with one measurement, because things are pretty multifaceted and complex. So just like I mentioned with depression, if we just do a self-report, it only gets at the person's view of their depression, and that's a pretty important part of it. But if we looked at their behaviors, if we've looked at physiological components, we get a better picture of their depression. If there's a Campbell and Fisk, very classic article, multi-method, multi-trait system, multi-trait, multi-method, and they're talking about you should measure things multiple different ways, and that's an important thing to really think about. The other part is we want to have a coverage of our construct. So with depression, a one question measure would be, are you blue? But we also want to get at the other components of it. So I've got a target here. We want to hit all parts of that target. So are you fatigued? Are you having problems sleeping? Changes in appetite, thoughts of hopelessness. So we want to hit all over that target of that construct, not just in the center with are you feeling blue? And then we also, when we do latent variables, we also get to pull out some of that error, which is a really big component of things. You know, we might have people who say yes to every item on a questionnaire because they're really wanting help, and we can pull that error out to some extent, the things that aren't related to depression or our construct of interest. So I just wanted to go over the symbols that we're using, and I've already mentioned these. When we have squares, we're talking about things we want to measure, or I'm sorry, things we've actually measured. So these are observed variables, sometimes called manifest variables, things we've measured. Latent variables or circles are things we wish we could measure. So these are things we want to uncover, but we can't actually measure directly. So again, depression is a construct. We can't measure it directly. Anxiety is a construct we can't measure directly. You're not going to see a lot of triangles, but I'm going to use it. We use it in the matrix algebra behind this, where we're trying to get at means or other things where it's a constant, basically. So I'll show you one example with that, but we probably won't see a lot of triangles as you go through, nor will you see triangles in the research that often. We'll also see these arrows, and just like a regression, this gets at prediction. So we're thinking of x1 predicting y1. When we talk about this, it has this little weird thing with the nomenclature where you're actually going to say y1 is regressed on x1. So it kind of goes in reverse of the direction of the arrow. And I don't know exactly why that is or why that's the case, but we're always talking, it's something that's in the syntax that we're going to learn, and so just kind of something you'll hear me say y1 regressed on x1. The other thing we'll see are these double-headed arrows, and these get at either a correlation. So on the bottom here you have x1 correlated with x2, or if that's pointed to itself, it gets at a variance. So a variance in x1, there's some sort of variation that kind of gets at, there are a bunch of individuals and there's variation in the score. Or same thing with a factor, there's variation. Not everybody has that same score for the factor. We expect there to be variation in how much you have of that factor, or how much people have of that factor. So here's an example, an overly complicated example with regression. If I didn't have this triangle, it would be a much simpler drawing, but basically we've got all observed variables, things that we've measured. So x is measured, y is measured, and we think x predicts y. And to say it correctly, y is regressed on x. And again, that's that backwards way of saying it. So x predicts y is easier to think about. We've got some leftover, and when we talked about it in regression, we talked about residual. So we've got part of y that's not predicted by x. So this is our residual here, and you notice the double-headed arrow. There's variance in that residual. So some people are predicted perfectly, some people are predicted not so well. So there's a variance in how much error there is in that person's prediction. On this side, there's a variation in X. People have different X scores. And then what I did with the triangle to just make this complete is we predict, and this is a constant, so we get that intercept. So this gives us the intercept, and then this regression coefficient on top, the beta 1 is our slope variable. And then we also get a mean, but it's not that important. So when we write up the syntax for this, we're never actually going to write up this one. I'm just putting it in this drawing to make it complete. But in general, the software will just put the 1 in there and give us these numbers that we need. So we don't actually have to do this component on the bottom. But I wanted to have that in there to make it a complete drawing. All right, so last week we talked about exploratory factor analysis and confirmatory a bit. We're going to talk more detail about confirmatory this week. And then this is a diagram that really gets at the difference between the two. So exploratory, every variable is loaded on every factor. And what we're trying to figure out is if this variable is more related to factor 1 or factor 2. So we got a factor loading score. If this is a 0.02 on factor 1 and 0.65 on factor 2, we think this variable loads on factor 2 and not on factor 1. And each one of these loadings will see where it loads on which factor. And in simple structure, it loads on one and only one factor, but sometimes we get weird items like we talked about last week, maybe arithmetic on the waist. Sometimes it loads on multiple factors. But with exploratory, we're allowing every variable to load on every factor. Confirmatory, we're not doing that. So we know that y1 loads on factor 1, y2 loads on factor 1, etc. And it doesn't load on factor 2. There's no loading of y1 on factor 2. So we have a model in mind already, and this is based on theory, or it could be based on somebody else's exploratory factor analysis. So we're setting this model up this way. We're not trying to figure out the factor structure as we did in exploratory. So confirmatory, we have a structure already kind of in mind. So let me go through the steps of structural equation modeling. We're going to go through this with an example later on when we work through these. We'll go through how to actually do it. But let me go through the conceptual steps of what we're doing. So the first step is defining our model. And so we have a theoretical idea of what's going to happen with our model. We might have multiple ideas. So in some of the examples I gave earlier, there are pathways of prediction, and we might say, I think this predicts this other variable, but I'm going to test out whether leaving that prediction in is a better fit than leaving that out. So again, this is very different than the other statistical tests where we got a value, is this significant or not. It was those previous tests like ANOVA t-test, it wasn't ambiguous. It was significant, yes or no. In this, we're going to be looking for what is the best fitting model. So we're doing a lot more comparisons. Things are going to be relative to each other. So if we're trying to predict childhood outcomes, we're going to have different variables in our models and different ways of predicting that child outcome. And we're going to try to figure out what the best fitting model is for our data. So there's more subjectivity to this. And so we're going to define our models as our first step. Second step, if you might have to worry about this at times, but I would say that you don't have to. Hopefully you just create a model and you never have to think about this second step. But once in a while you'll see an error message that says you have a model that's de-identified. So what this basically means is, do we have enough information to calculate all of our parameters? So when we're creating a pretty complicated model with multiple predictions going in multiple directions or multiple factor loadings, we're trying to get a lot of information out of that model. So in order to get information out of the model, we have to put information in. And the information we're putting in is our variances and means and all of the information about the variables. So we have to put enough in to get enough out. So I'm going to go over that and again repeat that in a second, but just kind of one way to think about it. If we're trying to calculate this equation here on the bottom, so 5 equals x plus y. X could be 4 and y could be 1, x could be 3, y could be 2, x could be minus 5 and y could be 10. There's just many different solutions for this equation here. So it's unidentified. We can't find out what x and y are because it has infinite number of solutions basically. Whereas in this model over here, we don't have enough information to calculate 2 parameters. We only have one piece of information. So 5 is our one piece of information we have, but we're trying to calculate 2 parameters, estimate 2 parameters. Over on this side, we have 2 pieces of information, and we're still calculating 2 pieces of information, x and y. So in this, and let's say that we put in a 1 for x and a 4 for y, and then we do the same here. 2 times x would be then 2 for this and 4. So in this we can estimate x and y equals 1 and 4. Basically. So in this we've got 2 parameters that we're trying to estimate, x and y, and then we've got 2 pieces of information. So we're identified enough of our model. So if we create a model that's too complicated and we don't have enough information, we'll be under-identified or unidentified, and if we have just enough, then we'll be identified. So this is something that we could run into at times with some errors. There's a formula to calculate how much information you have, and then we would calculate how many parameters we're trying to estimate. And we'll get something called degrees of freedom, and degrees of freedom are how many pieces of information we have left over after we've estimated all of our numbers. So we want some degrees of freedom. We want fewer parameters than pieces of information. So let me just show you in this. So we have, without counting up all the pieces of information we have, we run into an identification problem. And what we can do, so we would have to estimate all of these parameters in this top model, and also all of these variances, this correlation, these variances, and so there's a lot of pieces of information to calculate. So what we'll do is we'll actually set this to 1, and when we set this to 1, we've now eliminated 2 parameters we're trying to estimate, and that it makes it an identified model. We now have enough information in this model to calculate all the parameters. So by setting this to 1, then x2 and x3 are relative to x1, and so if this is above 1.2, then we know it's above the loading for x1. And we'll go through this with some examples, and I'll kind of show you some of the problems. Another way we can do this is, instead of estimating all of the variances, we set this variance to 1, and this just creates a standardized factor. So almost like a z-score, this factor becomes standardized. So our variance is set to 1. And then we can estimate all of these factor loadings separately. So these are some decisions we have to make. If you don't do any of this, you'll still be fine. The software will estimate these and put these in, so it's an identified model. So again, this is just something when we start troubleshooting, we might see this issue pop up. All right, and again, the number of parameters that you have left, or the number of pieces of information that you have left over, that's going to be your degrees of freedom. All right, so the next steps of structural cohesion modeling, we're going to estimate the model, and the computer is going to do that. Just like exploratory factor analysis, there's different ways of estimation. Again, we'll probably let the software do the right default, but if you have something that's unique about your data, that we might want to set other estimation procedures. So if we've got a dichotomous type of variable or categorical variable, we'll change things, the estimation procedures. Then the next step after that is evaluate the model fit, and finally, once we get a good model fit, we'll look at the parameters and kind of discuss if they are meaningful, what they mean, and does our main outcome, is it predicted by our parameters? So it kind of tells, we have to interpret the model once we find the best fitting model. So let's talk about model fit. So again, with all of these models, we're making a guess as to how all these variables fit together, how they all relate to each other. So our guess is not probably going to be perfect. There's going to be leftover amount. We're not going to predict it perfectly. So we're going to try to see how well it fits. And one of the ways we can see how well it fits is to do a chi-square test. And with a chi-square test, we're going to look at the original correlation matrix or covariance matrix, and then what is recreated from our model. So the closer these are to each other, the better our fit is. So this is just one way. This shows up in all of our outcomes or our results. So you always see this chi-square. The problem with the chi-square is it's almost always significant. So as soon as you have a large sample, this is going to be significant. It says we've got, this fit measure is always significant. So it's not all that useful. So what we're going to end up doing is using other estimations of model fit, and there's quite a few of them, and usually they're all based off of this chi-square, and they're adjusting this chi-square. But what we're going to try to do is to have the best fit, so the best accuracy, but also have it be parsimonious with as few variables as possible. If we had everything predicting everything else, we would have a really good fit, but it really isn't parsimonious. It doesn't, not everything predicts everything else. So we're going to look at a lot of different fit indices, and some of these are adjusting, and they basically penalize if you have too many parameters, so if you don't have a parsimonious model. So this table I find really helpful. This came from a Rex Klein book, and I haven't seen this table replicated, so it's an older book. And what I like about this, it gives you suggested cutoff values. And these are rules of thumb. These are things that suggest good fit. This isn't like a statistical significance test where you say, yes, it was a good fit, or no, it's not. These are just ideas of where you should get a good fit. And there are different types of fit indices. So you've got incremental. So this is if you're fitting model that are nested. So with one model you have a parameter that's there, another model you have a parameter that's not there. You're going to see how much better fit do you get with the model, the next model. So I usually choose one of these or two of these, and often it's a CFI. So CFI, where it's closer to 1, is a better fit. Absolute fit is something that I always report as well. And for this, I'll usually report the RMSEA. And this one, the smaller the number, the better. So Michael Brown said if it's below 0.05, then you have a good fitting model. And so we're looking for a small number for that. And then there's these are interesting models of fit too. And I usually report the AIC or BIC. And these are going to be more relative. So if we're looking at models that are similar to each other, then we're going to try to pick the one that's closest to 0. And depending on the type of estimation we run, we get different. Sometimes we don't always get all of these model fits. We only get some of them. So we'll see AIC and BIC in different examples as we go through things. All right, and then here's kind of a summary of, let's say we're looking at these variables. These are all measured variables. We don't have any latent variables. And in this original model that the person hypothesized, you've got 2 variables: illness, symptoms, neurological dysfunction, predicting all of the other variables. in a different model, the predictions go in different directions. So for this diminished SES, it predicts neurological dysfunction. And so each one of these has something slightly different to it. Some only say there are correlations between these and don't try to do prediction. So what we'll do is look at model fit of each of these. And maybe we leave out one of the pathways in another model. We don't say that that's related to this other variable. So there's many ways to do this. So that's what we're going to do, is we're going to build a lot of models, adjust the model, and figure out which model fits the data the best. So in this example here, we could kind of imagine, let's say that we want to leave emotional coping out and we don't think it's related to resilience. We could just drop this path out and see if it fits better. I'm going to go through M+ when we go through the workshop. I just want to talk a little bit about the three basic statements that we have in M+. So when we're looking at M+, we have by statements, and by statements get at factors. So when we're talking about anytime we're creating a factor, we'll use a by statement. So what I've got here is a by statement, positive coping. So we'll type this out in when we use M+. Positive coping is indicated by acceptance, planning, positive framing, and active coping. And we can see this here. Positive coping is indicated by acceptance, planning, positive reframing, and active coping. So what we've done with this one statement, we've created this whole part of the model. We'll have to do the same type of statement. We'll have 5 different statements with by statements. So we'll have emotional coping by venting, self-blame, instrumental support, and emotional support. Another by statement, disengagement coping by humor, behavioral disengagement, substance abuse, religion, and denial. A 4th one, resilience by personal competence, family cohesion, social competence, resources, structure, style. And then a 5th one, stress domains by these 3 stress domains. So that draws out most of our model right there. So we've got 5 different factors, so we need 5 by statements. So factor by each of those. So it looks like a complicated model, but from a syntax standpoint, that's relatively simple to indicate how these factors are created. Another statement that we'll use in M+ are with statements, and with gets at correlation. So these are going to be our double-headed arrows, so correlation. And in this situation here, we have positive coping with emotional coping. So that's that statement right above. And then we have a second double-headed arrow here, emotional coping with disengagement. So we'll have to have 2 with statements in this model here. So we basically have the whole model created already with 7 statements. And then the final type of statements are on statements. So on statements are getting at regression. And this is the one that's the most confusing, because we have the arrow going the opposite direction. So resilience is regressed on positive coping. So it's not a mistake. It's resilience is where the arrowhead goes, is regressed on positive coping. And same thing, resilience is regressed on emotional coping. Stress spectrum domains is regressed on resilience, and it's regressed on emotional coping. So those get the rest of our arrows into this model. So with 10 sentences, I've drawn out this really complicated model. So I find the syntax with M+ not to be too difficult. So we'll go over that again in our workshop in much more detail. All right, so again, path analysis is a bunch of different techniques. Part of it is the factor analysis with the confirmatory factor analysis we just went over, but it's also path analysis, which is just a series of regression models. We've done this before. We've got this example here where exam stress and exam performance go together, but there are direct and indirect effects of this. So exam stress directly could relate exam performance, but indirectly relate exam performance through physical mental anxiety and through exam preparation. So we've done this already with mediation. The nice thing about structural equation models is we can build this all out in one model. This would be two separate mediator models. We have a mediator path down here and a mediator path up here, but with structural equation model we can do it all at once. So simplifying it, with regression we have one outcome and 5 predictors, and we can only look at one outcome at a time in each regression. With structural equation modeling, we can create this whole complicated model on the right hand side in one model. So y is regressed on x5 and x4. x4 is regressed on x2 and x3. x3 is regressed on x2 and x1. So if we look at this, we've got 4 different regression models that we'd have to write up just to get to this complicated model here. So structural equation modeling allows us to do much more complicated relationships and probably more real world like. We'll get into in the coming weeks just other things we can do. We can have categorical variables. We can look at multiple groups and see, do different groups of people have the same model? That maybe, for one group of people this model doesn't fit them as well. We'll look at interactions. I'll talk in much more detail about missing data. These estimation procedures allow for missing data, and it will use everything that you have available. So these are really valuable if you've got missing data. And we'll talk about structure of models. So if you've got kids in a classroom in a school, you've got 3 different structures. So the individual children in the particular classroom in the school, we can look at those 3 different levels and kind of break apart some of the variance associated with that. So we'll spend some time on these things later on. Sometimes when we model things, I mentioned just getting rid of a model or getting rid of a pathway. We could also say that pathways are equal. We can tell the model what the pathway should be. We can do nonlinear type pathways. Imagine relationships, they're not always linear. We've talked about this before. So we can make things nonlinear. And so we can do other things to the model to really test them and to come up with different models. All right, and then just again, we talked about maximum likelihood last week, when we were talking about estimation procedures for exploratory factor analysis. This is going to be an estimation procedure we're going to use in much of structural equation modeling. It's pretty much the default, and it allows us to calculate all of the parameters at one time. So this is quite a valuable thing. It also is a full information method, and what that means is it's not going to delete people who have missing data. So if a person is missing, they lost one of their self-report measures, that person's still in the data set, and all of that person's information is going to be used every place else. So it's really helpful if you've got missing data. It just uses what is available. And some other things that we'll have to kind of consider when we're doing this type of modeling, it's guessing at a bunch of different parameters at one time. And so if you've got a complicated model, something like that model that I've shown as an example, it's not that complicated. It's got 3 sort of predictions in it. But if we have something much more complicated, guessing all those parameters at one time can be difficult. It used to be that we'd have to create start values and kind of tell the software where to start their estimation, and it's a sort of an iterative process where they start their guessing, and then if they're close to it, they find it a little bit faster. We don't really have to do this that often anymore. I'll show you some examples where we might have to do that, but I put it in here just so we can know that sometimes we might want to do start values. All right, and then here's another example I'll go over quickly. Just this is we've got our confirmatory factor analysis. We're looking at things like familial risk being predicted by SES and psychopathology. So this is a CFA model, but we also have our regression model in here where one thing predicts another thing. So familial risk predicts cognitive predicts achievement. So this is the advantage of structural equation modeling. We can create latent variables with multiple indicators, and so this is a much better indicator of familial risk than just one of these. And then we can predict complicated regression models with this, where one leads to another, which leads to another, rather than all of them leading to one outcome. So this is kind of highlighting the advantage. This was a model that we ran a few years ago for the CDC. They were looking at willingness to participate in the vaccination trial, and there were different sites for where they collected people. This site difference was important because thinking about different groups of people, maybe there are differences in how people how much people have a willingness to participate in a trial. And you can kind of see some of the other things that we're looking at. It was an HIV vaccination they were looking at, whether they had stigma related to HIV, would that change their willingness to participate? The risk of getting HIV, so maybe if they're at higher risk, we might think they're more likely to participate, whether they're altruistic or there's incentives involved, or they think there's an impact to their community. It might lead to more willingness to participate. We're also looking at people of different ethnic backgrounds, and a big ethnic background we're looking at is people who are black. And in one of these locations, it was near Tuskegee, Alabama, where there was the Tuskegee study, and so maybe there's mistrust of getting a vaccination. So this was a big set of variables that was also being looked at. So all of this kind of looking at willingness to participate. So when the model's all complete, we can actually see the mistrust beliefs really didn't have much of an effect. And that was kind of one of their main hypotheses. And possibly maybe this is too outdated, of people didn't have knowledge of this as much. Maybe it didn't get at the construct that we're interested in as much. Maybe some of these variables didn't get at it as well. But whatever reason, this was not a good predictor of willingness to participate in a vaccination trial. Some of the facilitative factors had bigger coefficients, so maybe being more altruistic might have helped. And then we also see some differences in communities. So if you're at higher risk of HIV, maybe you're more willing to participate too. So again, this highlights a lot of different things we can do with these type of models. We can look at group differences. We can look at a complicated real world example of a variable that will people be willing to participate in a vaccination trial. So I want to show you the syntax to this model, and looks very complicated on the surface, and my syntax is a little bit less. It could be simpler, but basically what we're doing with the M+ syntax, you give it a title. You don't need to give things titles, but it just helps you remember what you did with this model. So, and this is not even that great of a title I gave. You tell M+ where the data file is. You tell M+ what the variables are. So these are all the variables, which variables you're going to use in this model. So if you're not using them all, just which ones do you actually use. And then the model itself, building the model. This is where I think it's much simpler than what that picture demonstrates. So perception of risk is indicated by, and I'll show you the syntax in a second, by sexual risk, likelihood of being infected, risk from current partner, and estimated risk. So it's indicated by these variables. The facilitative factors, altruism, incentive, support of the community, role overload. So that creates that variable. I've got some things here that aren't even needed anymore in M+. This is that I'm setting a variance to 1. That was to help me identify things. This is also setting a variance to 1 to identify things. These are also the same thing. So I don't even need to put these in. I'm doing that because M+ at the time, it just helped M+ along. Some of these other, so here's another factor, and then I put the regression coefficient. So mistrust is regressed on Tuskegee, and this other variable, trial information, this is the factor, and then the willingness to participate, this is the big one, is regressed on trial information, religious beliefs, mistrust, stigma, perception, and facilitative factors. So we'll go into much more detail about this. My intention was just to show you that the model statements are not that complicated. I just made it sound much more complicated than it actually is. All right. Another thing we can do is what's called factorial invariance, and this is something that I think is very powerful and meaningful that we should be doing more often. And this is the idea that the factor structure of measures might be different for different groups or different ages. So when we look at, and this is a quote by Thurston, and for some reason I just liked it, but do the factors change based on how old you are or the group you're in? So something like intelligence, it makes sense that as you age, intelligence as a factor changes, and that as we look at somebody who's 2 years old, number of words known is probably the biggest variable related to intelligence. But as you get older, things are different, and so the structure of intelligence changes. We might have groups that the structure changes for too. So this is an important thing. It's also important for measuring things over time. So if we find people have changed, is it the person or the test that has changed? And that to me is a really important thing, because the test could have changed to that person. And we need to make sure that the factors have stayed the same, or they're invariant over time. So here's an example. I'll go through this example pretty quickly, but and we can spend more time in the workshop going over this. But this is, let's say we're looking at different groups of people. And I'm going to use the anxiety sensitivity index that we used last week, and is it the same across different ethnic groups? So what we'll do is look at, is the configuration of the factors the same? So what we found last week in exploratory was a 3-factor structure, and do we have that same 3-factor structure for the groups? And if we don't, then maybe we have a 4-factor structure for one ethnic group, or something along those lines. We'll then look at going up to be more strict metric invariance, and do the factor loadings stay the same for every group? So do certain measures, like it scares me when my heart beats rapidly, is that the exact same for one ethnic group versus another ethnic group? And then the final level is, are the means of the factors the same for each ethnic group? So for one ethnic group, are physical concerns the same as mental, or as it is for another group? Mental incapacitation, is that different, the mean of that factor different for one group than another group? So we can really look at a lot of different levels of this factorial invariance. So let me give you the example. I should have broken this down in a few different slides, but what we did is we started to look at is there a fourth factor for some groups? And maybe there was a paper that listed that said people who report as African American, there's a four-factor structure. So we tested that versus the three-factor model, and we found that the three-factor model fit better than allowing a group to have four factors. We then tested whether these factor loadings were all the same. So we allowed them to vary for different groups. So does the model fit get better if we allow it to vary across groups? So for different groups, this might be a 0.7 for one group, a 0.3 for another group, and a 0.1 for the third group. So allowing these to vary, we're adding a lot more parameters to our model, so it becomes much more complicated. So that's something that's going against us, but does it fit the data better? So we want to check that by model fit. And then the final thing we allow to vary are the means of these factors. So do the means of these groups, do they differ based on ethnic group? So what we found, and I'll come back to the slide, we did these different models, we looked at model fit. There really isn't that much difference between model fit, but what we finally came up with was that the loadings are better fit if they're all the same across groups. So then we looked at the means, and we found that it was a better fit if we allow the means to vary across groups. So what we found, and in this example here, we set one group to 0, and then we wanted to see if the other groups are different. So we found that for mental incapacitation, people who self-reported as Hispanic, and these are college students, the University of Virginia, so they're self-reporting being Hispanic, and they reported higher amounts of mental incapacitation concerns. It's not a clinical group, so that's something to keep in mind. For social concerns, we had people who indicated being Asian, having more social concerns, showing other people their anxiety. And then physical concerns was higher for people who reported being African American. So it's kind of an interesting type of model to look at how groups might differ. And I think that's an important thing we don't do often enough. We say, this is the model, these are the constructs that are in that model, but we don't look at the differences between groups. So this starts to get at those individual differences. We're going to get even better at individual differences. To label a whole group and say that a whole group of people have more mental incapacitation is maybe still not the best way to look at individual differences. We've got variance here. So even within the group of people who report to be Hispanic, there's a lot of variation, and that's what we really need to break down. So we need to get to that level, and that's where we're going to get to in the next couple weeks, where we're starting to look at individual differences, and we can break apart, and instead of just labeling people with a group and saying all people that are of this group are a certain way, we can start breaking those individual differences down even more. So that's where we're going with this model.